For this one here, 4.5 deals with integration techniques by substitution. Evaluate integrals using substitution and solve applied problems involving integration by substitution. Here's our first example here. We're asking us to integrate this particular function. We notice that 2x is the derivative of x squared, and when we look at this integral here, we see the 2x, we see the x squared, so we can identify here. What we see is our u function can be, our u function here is x squared, so the derivative of x squared is going to be 2x dx. So we can move stuff around. So now we have it in the form of u du, in the form of integral of u du, like that. Or we can take the integral of u du. Okay. In this case here, we end up with a function, a particular type of function of e to the u du. So we can look up the table or recognize what it is, and you know that the exponential is the same thing as itself. So we end up with e to the u plus c. And then we can rewrite it here because we're dealing with x. End up with e to the x squared plus c for our final answer. Let's look at another example here. These are some types of substitutions. Okay. You can rewrite it in terms of a u to a power. We can have e to the u du, 1 over u du. All of these u's here could represent a function with the derivative. So the strategy here is we want to rewrite it in terms of the derivative. Some form of rewrite it into some form of with some form of f prime of x dx. Make sure everything is represented. Then we can go ahead and integrate it. Okay. And that's what we have in the first example. We have our f prime of x and we have the dx part of it. So we can go ahead and integrate it. So let's look at another example here. In this case here, notice that 3x squared is the derivative of x squared plus 1. Okay. So we can let our u be, x to the third plus 1. So our derivative of that would be 3x squared dx. Now we can move stuff around so we can see the u part there and the du part there. So what I have here is really in the form of the integral of u to the 10th du. Now we can integrate that function there, the u function, and then substitute back in. And it gives us for our final answer. And here's another one here. Notice that 4x is the derivative of 2x squared. Okay. So we can let that be our u, and the du is this right here, 4x dx, and I have that up there. I don't have to change anything. So I have a u and a du there, so I can rewrite it in that terms. So power rule, I can integrate it, so I end up with u to the 4th over 4, and then I can rewrite it because I know what u is. So I know what u is. Look at another one here. In this case here, notice that 2x is the derivative of 1 plus x squared. So I can see here that my u is going to be 1 plus x squared, and my du is 2x dx, which I have in the integral. So I can rewrite that as 1 over u du. And if you remember from my tables, that goes with the ln function. So when I integrate it, I end up with ln u plus c. And I can replace the u with 1 plus x squared. 1 plus x squared. Yeah. And that's our final answer there. Here's another one. Notice that 2x is the derivative of 1 plus x squared. So that tells us what our u is and our du. So in this case here it's different. I have 1 over u squared du. I can rewrite that in terms of a power function. U to the negative 2 du. Then I can integrate it, and I end up with a negative u to the minus 1. Okay. My final answer there, that u belongs on the bottom, so I have a negative 1 over 1 plus x squared plus c. This one here, you notice that 6x squared is the derivative of 3 plus 2x to the third. So my u is going to be, that's my u, it's going to be 3 plus 2x to the third. My du is going to be 6x squared dx. And I have that up there in the numerator. So I can rewrite it. Now I have a f of x dx there. So I can rewrite it and say u to the minus 1/2 du. I have a power rule there. So I can integrate it, and I end up with 2u to the 1/2 plus c, which is 2 times the square root of u plus c. Replace the u with 3 plus 2x to the third, and it gives us the final answer there. Here's one here. Okay. Notice that the derivative of ln x. Did I state that right? Yeah, this is written kind of interestingly. So notice that the derivative of ln of 3x is going to be 1 over 3x times 3, 1 over u du, which is going to be 1 over x. Okay. So let me write it up here. So what you really have there is ln of 3x times 1 over x dx. So now you can see your u du. So that simplifies to 1 over x. So that's what I have there. So you can identify your u, and there's your du. Okay. So I have the integral of u du there. So I can rewrite that as u squared over 2 plus 3. Okay. And then I can plug back in and integrate it. Plug it back in, end up with ln of 3x quantity squared over 2 plus c, my final answer. And this one here, number 8. Okay. And this one we have an exponential. So in this case, my u is x squared. So we expect du to be 2x, but when I look in the problem there, I don't see a 2. Okay. So what I end up having to do here is that I have to fix it. So what the integrand contains is x dx. I need a new factor of 2. So what I end up doing is multiplying a 2, and I compensate by multiplying by 1/2 on the outside. So it balances out. Now I have my u du there. So when I look at it again, I have 1/2 the integral of e to the u du. Then I integrate it, I have 1/2 of e to the u du. Then I replace it. Here's another one here. In this case, I'm letting my u be 4x squared. So I would expect to find a du of 4x to the third. I mean, that should be a 3. That should be a 3. Okay. There. That's supposed to be a 3. So I expect my du to be 12x squared. When I look at the integrand, I don't see a 12x squared. I see a x squared dx. We need a new factor of 12. So what I end up doing is I end up multiplying by multiplying a 12 here and compensating by on the outside, making it a 1/12 so that they cancel out. Then I integrate it. I have my u and du. Okay. And I integrate it and end up to 1/12 e to the u plus c, which gives me 1/12 e to the 4x to the third. In this one here, notice that dx is the derivative of x to the third. So what I have is 1/u du, and that becomes the log. And then I end up with ln u plus c, replace u with x plus 3. There. Let's look at another one here. Here I have x to the, this is example 10. In this case here, the derivative of x squared plus 3 is 2x. In this case here, when I look at it, I would expect it, I don't see a 2. I see the x part, but I don't see the 2. The 5, I think, is extra, so I move that factor of 5 out. Okay. So I have my x dx there. So I need a new factor of 2. So I multiply by 2, and I compensate by multiplying by 1/2 on the outside. And then now I have a u du there. I integrate it. I end up rewrite it here with an exponent, u to the 1/2 du, have a power. So I end up with 5/2 times 2/3, u to the 3/2 plus c. And that simplifies. Okay. Then I replace that with my u with x squared plus 3. And now I have to evaluate it for a particular interval. Okay. So I evaluate for a particular interval. I replace the x's with 1s and 0s and subtract. And it simplifies to being 4.673 for that one. And as a summary, integration by substitution is the reverse of applying the chain rule. substitution is reversed after the integration has been performed. Results should be checked with using a differentiation.